Hi, Lawrence Krauss here again. I'm back for the Origins podcast, part two of talking about the anomalous magnetic moment of the muon, or the gyromagnetic ratio of the muon, the ratio of its magnetic moment to its spin angular momentum. Now, I talked about in part one about the classical calculation and the quantum mechanical calculation for the ratio of the magnetic moment to the angular momentum of the muon or electron. Showed you that Dirac showed that ratio should be twice as big as it should be for a classical particle. And then when we have quantum electrodynamics, which takes into account virtual particles that pop in and out of existence, and we know to be there, when you include their effects in the calculation, it changes the result by 1 part in 1,000. And that prediction has been now calculated to 14 decimal place accuracy for electrons and 10 decimal place accuracy for muons, with the primary uncertainty for muons being the fact that you can have virtual loops of virtual quarks in the calculation, and those virtual quarks interact strongly to produce particles like protons and neutrons, and the strong interactions can't be calculated easily or directly because the interactions are so strong. So we have to use experimental techniques to try and estimate the size of those effects in the theoretical calculation. And they produce a dominant uncertainty, which allows you to make a prediction that is accurate to 1 part in about 10 billion or so. And so if you want to compare theory with experiment, you have to be able to do an experiment that's accurate to 1 part in 10 billion or so. And those experiments have been done ongoing for now about 70 years and have improved to the point, I'll want to take it this way. Sorry. To the point where we can now measure the levels of this accuracy. So the way we measure, as I showed you before, the way we measure a spin magnetic moment, the size of the magnetic moment of the muon or electron, since it has a spin, and we want to measure the size of this magnetic moment, we see how that spin precesses in a magnetic field. And the rate of precession is proportional to the magnitude of the magnetic moment times the magnitude of the magnetic field you're applying. So to make such a measurement, you have to have a well-known magnetic field that you can calibrate precisely, and then you have to be able to measure the spin precession frequency accurately. And if you can do both those things to an accuracy of 1 part in a billion, then you're golden. Now, to measure the spin precession, you can do two different ways. If the spin is precessing, then it will absorb or emit electromagnetic radiation at the frequency of the precession. So you can try and basically check for absorption or emission of radiation at a specific frequency and measure that frequency. And that technique has been used. But the other way is to try and measure the spin precession directly. And that's the way it's been done at Fermilab, following on an earlier experiment at Brookhaven National Lab. The Fermilab experiment uses the same magnet that was used at another laboratory, Brookhaven National Lab in Long Island, over 20 years ago to measure. But Brookhaven now is not operating with its accelerator anymore in a domain that can do this experiment. So they moved this incredibly massive superconducting magnet with a magnet that has incredible accuracy, incredible uniformity over a large region, many meters. And they moved it overland and by sea, by lakes, if you wish, to eventually to get it to Chicago, to get it to Fermilab. And then they do this following experiment, which I'll try and describe. I should indicate that with my takeout dinner, I had a margarita, so we'll see how this goes. Okay. So the Fermilab accelerator produces very high energy protons. And then if I smash those protons into a target, lots of elementary particles come out, a whole splash of them. Among them will be muons, actually antimuons, positively charged muons, that are like positrons, but the antiparticle of electrons, but in this case, muons, as I say, are 200 times heavier, and their antiparticles have the same mass. So you get muons and their antiparticles, but in this case positively charged muons coming out from the protons. And then you can select the muons and try and collimate them with a certain energy, and also make sure their spin is going in a certain direction, so-called spin polarized muons. So you basically have muons coming out with their spin more or less aligned in the direction of their motion. Then you could direct those muons into this experiment. The experiment involves a big magnet. Now, if you take charged particles and you have them move in a magnetic field which is perpendicular to the direction of their motion, then we know that charged particles will go in a circle. So you can ensure that these muons will go around in this circle. Well, if I could do it well. And they go around in a circle of known radius if they have a known energy. So they're going around in a circle, but because of the magnetic field, which is also pointing in a different direction than their spin angular momentum, basically their magnetic moment, the magnetic moment will precess, their spin will precess. And so as they go around that circle, the spin will precess as well. Now, there are a few things you need to know, and there's about muons, and they're very interesting and amazing. Muons don't last forever. Electrons are stable, but muons, that looks like this isn't quite in focus again. We'll wait till it comes in focus. Come in focus, camera, please. There we go. Try and get it to jump into focus. There we go. Muons last about a millionth of a second in their rest frame. But these muons are traveling at the speed of light, and therefore time is dilated for them, and therefore they last much longer as they're traveling through this thing, and they go around this many times before they decay. But when they decay, a muon will decay into a positron and it turns out two neutrinos, an electron neutrino and a muon neutrino. So I'm going to write this down. But one thing we know is that some other remarkable aspect of muons is they decay in a very special way, which is due to a property of the weak interaction called parity violation. Parity violation means that the weak interaction can basically tell the difference between left and right. And one of the ways it was first discovered that the weak interactions violate parity, and a Nobel Prize was won for the prediction, not the measurement, it turns out, but the prediction, by two guys named Li and Yang in the 1950s. If a muon is at rest and its spin is pointing in a certain direction, its spin magnetic moment is pointing in a certain direction, the same direction as its angular momentum, as it turns out, then it turns out when it decays into electrons and neutrinos, the electrons will be emitted preferentially in the same hemisphere in which the spin is pointing, in which the spin magnetic moment is pointing, or the angular momentum is pointing. So if the angular momentum is pointing up, if the particle is spinning like that, then more electrons will be emitted in that direction than that direction. Now that's if it's at rest. But what if the muon is moving? If the muon is moving, then it means more electrons will be emitted in the same direction as it's moving than in the opposite direction. But if the spin is precessing, then what will happen is the amount by which electrons are emitted in the same direction as the motion will change over time. And that means that since the electrons that are being emitted in the same direction as the motion of the muon will have more energy of motion than those that are emitted in a direction which is slightly different than the direction of the muon, because they'll be traveling a little less fast. So the ones that are emitted in the same direction will be traveling faster, and the ones that are emitted in a slightly different direction will be traveling slower. And that means if you measure the energy of the outgoing electrons as the spin precesses, you'll see it vary. The energy will oscillate back and forth at the rate at which the spin is precessing. And that's what the experiment measures. It looks at electrons that are emitted at different points around this ring as the muons decay at different times, because they don't all decay at exactly the same time, and the spin is precessed by a different amount at the different points on the ring. And then by measuring the energy and seeing that the energy oscillate, and measuring the period of those oscillations precisely to a part in 1 part in a billion, you can try and measure the precession frequency. And once you measure this precession frequency, it's, remember, calculated to be the product of the magnetic field times the magnetic moment of the muon. Then you measure the magnetic moment of the muon. And that's what has been done at Fermilab. The experiment's taken many, many years. And again, it was first performed 20 years ago. And with a certain accuracy, it disagreed with theoretical predictions, but its accuracy wasn't great enough to really write home about. But now, 20 years later, the new experiment just reported their results 2 days ago, and it can be given this way. The gyromagnetic ratio of the muon is 2. Remember, it's 2 if it were just a Dirac particle, times 1 plus a muon, where a is a very small number. Theoretically, in the standard model, we predict a to be a number which is basically 116,591,810 plus or minus 43 times 10 to the minus 11th, or about 1 part in 1,000. But all these numbers here are significant. This experiment, when combined with the previous experiments, gives a number that's 116,592,061 plus or minus 49 times 10 to the minus 11. So the difference is 251 plus or minus 59 times 10 to the minus 11. And that difference, if you turn out if you take the difference of the theoretical uncertainty and the experimental uncertainty, if you just look at the experimental uncertainty and compare it to the theoretical prediction with its uncertainty, you find out the difference is 4.2 sigma. Sigma. Now, what's sigma? Sigma is a measurement of your confidence that you're in your result. And this says that this is over 4 sigma. The theoretical prediction is over 4 sigma away from the experimental result. 4 sigma tells you that the probability that those two numbers agree is smaller than 0.3%. So there's 3 possible explanations for this difference between theory and experiment. One is bad luck. If you work it out, about 3 times out of 1,000, if you perform this experiment 3,000 times, one of those times you might get a result that differs by 4.2 sigma. So maybe it's just really bad luck that you perform this experiment once, and that time happened to be unlucky at a level of 3 parts in 1,000. That's one possibility. That's why in particle physics we usually use 5 sigma as the golden sort of number for a discovery, because 5 sigma says that the likelihood of theory and experiment disagreeing at that level is smaller than 1 part in almost 100,000, and that we figure is enough to say it's so unlikely that it's probably not the case. But it could be bad luck. But remember, it's not likely. It's a few parts in 1,000. Another way of putting it, it's 99.7% likely that there's a distinction between the theoretical prediction and the experimental result. The other possibility, which is what's caused such interest and why it's in the news lately, is remember that the calculation allows for the exchange of virtual particles, and the photon loop the photon that's traveling in that loop can spontaneously turn into a particle and an antiparticle, which then annihilate again and turn back into a photon. And all possible particles and antiparticles come in this loop. Each contribution, the heavier particles have a contribution which is suppressed by 1 over their mass. The heavier particle effects are very, very small. But if there are new heavy elementary particles that haven't yet been discovered in accelerators, they could contribute. Now, this has been known for many, many years, and as I talked about in a recent tweet, many people, including myself, did calculations, and we, for example, showed that one of the most popular theories beyond the standard model, called the supersymmetric standard model, or Susi, uh, gives predicts a whole bunch of new particles, and they will contribute to the magnetic moment of the muon. And I think now, well, 1983, 38 years ago, we calculated those effects. But there have been lots of other possibilities with other particles that have been calculated. And so if this difference turns out to be real, then it might point at the discovery of new particles beyond the standard model of physics for the first time, telling us that there really is new exciting physics and new fundamental particles, which might explain a number of outstanding problems in fundamental physics right now. And that's the most exciting possibility. The first possibility, of course, is bad luck experimentally. The last possibility is bad luck theoretically. Because remember, I told you that the biggest uncertainty in calculating the magnetic moment of the muon comes from this. I'll use this finger because that's more used to doing this now. Comes where the photon turns into quark and anti-quark pairs, and you have to use a strong interaction physics to predict, to calculate this effect. You have to actually measure this effect in other experiments and try and use it in this calculation in order to predict the result, and it gives the dominant theoretical uncertainty. What if it's wrong? Well, it turns out recently another mathematical way of trying to calculate this effect is not using fundamental mathematical methods, but rather reproducing things on a computer, turning space-time into a lattice, and basically doing computer calculations of the strong interaction directly in a way you can't do analytically, mathematically, with very sophisticated computers and running what's called a Monte Carlo and trying to calculate the magnitude of this effect. That's using something called lattice QCD, lattice quantum chromodynamics, or lattice gauge theory. The kicker is, recently, this has been done, now that we have new higher power computers, been done more accurately, and the new result using this calculation actually agrees much more with the result of the experiment than old calculations. Now, many different calculations have been done, and so they're in disagreement with this lattice gauge theory calculation, and so maybe it's wrong. But the new result from lattice gauge theory tells you that if you calculate this diagram, the effect of this effect really on the magnetic moment of the muon using lattice gauge theory, you come out with a theoretical prediction which is much closer to the experimental result. So perhaps it's theoretical bad luck, and perhaps when we know the theory better, the two will agree and the standard model will once again reign supreme. We don't yet know. So what's next? Well, only 6% of the data has been yet analyzed from this new experiment. And when all of the data or more of the data is analyzed, the error bars will go down. And if the error bars go down and the central value remains the same, you'll get above 5 sigma. And that'll tell you it's really, really hard for the theory to agree with the experiment. So if the experiment continues and with more data and the uncertainty gets smaller, but the difference remains the same, it'll really suggest new physics. Another possibility is the LHC. Why the LHC? Because if there are new elementary particles that are heavy, we may discover them directly at the LHC. And so we might discover heavy particles at the LHC, like supersymmetric particles, which will then explain this result. And the final result is we'll do the theory better. Lattice gauge theory calculations are improving, other calculations are improving, and maybe the uncertainty in the theory will go down. And that's where we're at right now. We're temptingly close to discovering something wrong with the standard model of particle physics, which has reigned supreme now for well over 60 years. Yeah, 60 years. And well, at least 50 years. 60 if you go back to when the first parts of the standard model were developed. 50 years if you consider by the time the standard model was completed. But no experiment in those 50 years has really pointed definitively for new physics. But if this disagreement continues, then and the theoretical calculation basically remains the same and isn't shown to be wrong, and the experiment gets better and better accuracy, and that disagreement continues, we'll know that there are new fundamental particles, new fundamental heavy particles in particle physics that will go a long way to telling us about the existence of new possible forces, and perhaps revealing and solving several fundamental problems, not just in our fundamental understanding of the structure of matter and the forces that govern the structure of matter, perhaps also to understand the physics of the early universe, which of course, for which this physics is relevant. So it's quite an exciting time, and hopefully that explains the theory and the experiment, which have been discussed briefly in the media, but the things are normally so complicated that they don't go into the details. I went into the details, and hopefully it wasn't so complicated that you can't understand them. So there you go. That's it. I hope you enjoyed it, and now you know where we stand at the forefront of particle physics. Take care. Lawrence Krauss for the Origins Podcast.